Let's imagine that we have a U-shaped tube that is open at both ends. So we've got an opening here and an opening here. And we put some fluid into the tube. So the fluid level comes up to some level over here and comes up to some level over here. Well, what level will it come up to over here? Well, let's just think about that for a second. We know that if this is open here, the pressure at this surface must be the atmospheric pressure. We'll call that PO. If we go down by some height h, we're going to increase the pressure by a rho gh. If we come across here at a constant height, we're not changing the pressure, so we've got a pressure over here, again, P naught plus rho gh. If we then go up a height h, the pressure will decrease by rho gh, so we must come back to a pressure over here at PO, so we must increase by the same height to get to PO, which means these two heights have to be the same. If the pressures are the same, PO and PO, if we go down h to get back to PO, we must go up h, so the heights have to be the same. Okay, very good. So we've got this open tube, open at both ends. We put some liquid in. That liquid must come to a constant height. Now let's imagine we close off this tube. Maybe we put some container on it here. If that pressure is still PO, then the heights of the liquid will still be the same. But let's imagine we increase this pressure. We increase this pressure to some amount P. So P is greater than PO. What's going to happen? Well, it's going to push down on this liquid, and this liquid will then go up. So let's imagine this gets pushed down to some new level down here, and then up to some new level up here. Well, now, we know that the pressure at the top, because this is still open, the pressure up here is still atmospheric pressure, PO. If we come down an amount to this height, the pressure down here must be PO plus rho gh, where this is some height h. And then if we come down and then back up the same amount, the pressure over here must also be PO plus rho gh. Which means the pressure that we have up here, whatever this pressure is, P, is going to be the same as what the pressure is up here. All of this is at the same pressure. Let's assume that what we have in here is maybe a gas or something like that. So we have a gas in here with a very, very low density. So the difference in pressure from the top of the gas to the bottom of the gas is very slight, not as much as by the change in the pressure in the liquid. Sorry, I should have mentioned that. Let's assume that we've got some gas in here that is low density gas. What that allows us to do is then to determine what's the pressure in the gas by measuring this change in height in the column over here. What's the difference in height from the level of the liquid over here to the liquid over here? And that increase, rho gh, will tell us the amount of pressure increase in the gas that we have above atmospheric pressure, P naught. That is very, very good. This actually will allow us to measure pressures in here by measuring the change in the height over here. Okay, very good. That previous idea allowed us to measure an unknown pressure relative to atmospheric pressure. So the interior container had a pressure higher than atmospheric pressure that was equal to rho gh, the difference in height. Let's take a look at a slightly different idea. Let's take a tube, but now one end is closed, and we'll put this down into a liquid like this. Now, if the pressure in here, inside the tube, is atmospheric pressure, then we expect the height of the fluid outside the tube, where the pressure is PO. So over here we have a pressure of PO. And if the pressure inside is also PO, we expect the level of the fluid to be the same. So the pressure in here is PO. And again, we're thinking of having a gas in here so that the change in height of the pressure in the gas is very, very small compared to the pressure due to the liquid. Okay, now what happens if we remove this air, remove the air in here, so that now the pressure inside is 0. In other words, we have a vacuum. So there is no atmospheric pressure inside the tube. Well, what's going to happen? I just put a hole inside of our tube. What's going to happen? Well, in here, there's no pressure here. So there's more pressure from below. That's going to force the liquid up the tube. And the liquid will go up the tube, let's say to some height. Well, how high is it going to go? Well, if we start here where the pressure is 0, and we come down a height h, the pressure down here will be PO, the inside pressure, but that's 0, plus rho GH. Rho GH, where rho is the density of the liquid in here, this liquid. So this has got a density of rho. The pressure here will be rho GH. But if we then come down a height and over and then back up that same height, we've got to come back to the same pressure we had here. So whatever the pressure is right here, that's going to be PO. So this is our exterior atmospheric pressure. Well, what does that mean? The exterior atmospheric pressure is directly equal to rho GH, the height of the liquid. So this is actually a way of measuring atmospheric pressure. Atmospheric pressure is sometimes called barometric pressure, and so this is called a barometer. Whoops, barometer. It measures atmospheric pressure. And when we have a high density pressure day or low density, this level will go up or down. And so the pressure is going to be directly proportional to the height of this liquid. So early measurements actually determined the pressure in terms of the height of this liquid. Now, let's think about a problem with this. If we were to make this with water, how tall would this be? Well, we already know that. 1 atmospheric pressure, what's the height that would give us atmospheric pressure with a density of water? Well, we already calculated that. That's 10.3 meters. So what's the problem with making this barometer with water? Well, it would have to be 10.3 meters tall. In other words, about 31 at least feet tall, 31 feet tall. Also, if you had this outside, it would only work during the warm days. If you had a cold day where the temperature was below freezing, your barometer would freeze and likely break it if it was glass or something like that. So this has been solved, both of these issues have been solved by using a higher density liquid that doesn't freeze as easily. And what do you think that might be? Well, mercury. Mercury is much more dense and does not freeze until a much, much lower temperature. And so mercury was used for these types of pressure measuring devices, so that the height or the change in pressure was actually given in terms of inches of mercury or maybe even millimeters of mercury. Those were actually used as units for pressure from the height of the tube or column of mercury. Perhaps if you've been in a doctor's office, I know I used to see these, I haven't seen one in a while, but when they take your blood pressure and they put a cuff around your arm and increase the pressure, on old versions there actually was a scale on the wall where you could actually see that column of mercury going up in the tube. And that was actually exactly what was going on here. That the pressure was forcing that column of mercury up the tube so that the pressure in the cuff could be measured. Okay, very, very good. Sorry, I forgot to tell you something. Those pressure cuffs that measure your blood pressure, those are called a sphygmomanometer. It's one of my favorite words, sphygmomanometer. All right. Let's take a look at another application of this variation in pressure due to depth in a liquid. Let's imagine that we've got a container here with some liquid in it, and what I want to do is I want to look at a small section, a small volume of that liquid within our container. So let's imagine that we've got some volume, and I'm just going to draw a cubic volume just for the sake of simplicity. So here's some volume of liquid within the rest of our liquid. Let's assume it's got some mass m. We know because the bottom is at more of a depth than the top, there are going to be different pressures on the top and the bottom. A higher pressure on the bottom, lower pressure on the top. Assuming that the areas are the same, that means that the force acting on the top, we'll call that F1, is less than the force acting on the bottom, we'll call that F2. So the pressure at the bottom is greater than the pressure at the top because we're at a greater depth at the bottom than we are at the top. There's also a force acting on this volume of liquid due to the weight of the liquid. If it's got a mass m, we know that it also has a weight that's going to equal mg. Gravity is pulling it down. Assuming that this fluid has been sitting here for a while and is not moving and is stationary, we know that that section of fluid must be in equilibrium. In other words, the net force acting on it in the, let's say, the y direction must be 0. So what is the net force acting on it in the y direction? Well, in the positive direction, we have F2. In the negative direction, we have F1. And we have mg in the negative direction, so minus mg. So we know this all must be 0 if this thing is not accelerating, and we're assuming it's not accelerating, we're assuming it's stationary, so that must be 0. Which means F2 must be equal to, bring this over here, F1 plus mg. What does this mean? It means that the force on the bottom, due to the pressure on the bottom, has to balance the pressure on the top plus the weight of the fluid, the weight of this volume of fluid. Okay? Well, that makes sense. So, as we go down, the pressure increases, and we can think of that increase in pressure because it's got more fluid to support above it. Great. Let's just keep that in mind. So, F2 equals F1 plus mg. And what is mg? mg is the weight of the fluid. All right, very good. Now, what I want to do is let's imagine we take out that fluid and we replace it with a block of some material, but that is exactly that shape. Okay? So, take out the fluid, put in a block of that shape. Let's do that.